Hello students, today we shall introduce ourselves to the chapter Real Numbers of class 10. In this chapter, we shall look into 4 major concepts. First one is about Euclid's division lemma. Second is the fundamental theorem of arithmetic. Then comes revisiting irrational numbers and then revisiting rational numbers with their decimal expansions. Before we look into Euclid's division lemma, let us recall the type of numbers we have studied till now. What are natural numbers? All the numbers used for counting 1, 2, 3, 4 are known as natural numbers. Then came the need of 0 and we added 0 to the set of natural numbers. That gave us set of whole numbers. After we were introduced to positive numbers and 0, there came the need for negative numbers and we call them set of integers. So, integers are negative numbers, positive numbers along with 0. After that, we have also studied what are rational numbers. What are rational numbers? Any number which can be expressed in the form p by q, where q is not equal to 0 is known as a rational number. Then we also refer to irrational numbers. What are irrational numbers? The numbers which we cannot represent in the form of rational numbers are known as irrational numbers. So, we are dealing with real numbers. Real numbers consist of rational numbers and irrational numbers. In this, Euclid, father of geometry, has given us very interesting division lemma. Let us look into what is this division lemma. In this, given positive integers a and b, there exists unique integers q and r satisfying a is equal to bq plus r and r is greater than or equal to 0 and less than b. Lemma is a proven statement which is used for proving another statement. Then what is an algorithm? Algorithm is a series of well defined steps, that is step by step process which gives a procedure for solving a particular problem. So, students, let us look into Euclid's division algorithm. To obtain the HCF of two positive integers, say c and d, with c greater than d, follow the following steps. Step 1, apply Euclid's division lemma to c and d. So, we find whole numbers q and r such that c is equal to dq plus r and r is greater than or equal to 0 and less than d. Step 2, if r is equal to 0, then d is the HCF of c and d. If r is not equal to 0, then you apply the division lemma to d and r. Step 3, continue the process till the remainder is 0. The divisor at this stage will be the required HCF. Now, let us solve some questions of your NCERT textbook to understand this process. So, students, let us look into your first question of exercise 1.1, which demands to find HCF using Euclid's division lemma. We have two numbers here, 135 and 225. The first step we should do here is we should locate the smaller number. 135 is less than 225. So, 135 becomes the divisor and let us divide 225 by 135. I think it goes one time. We have remainder as 90 here. We will again take 135 and divide it and we get 45 as the remainder. Because the remainder is not 0, again we will continue the process and we will divide 90 with 45. And what do we notice? Yes, now we get the remainder as 0. As we get 0, the division stops here and the last divisor, that means the divisor at this stage becomes the highest common factor. Let us see how we can calculate highest common factor using Euclid's division lemma. we have the numbers 135 and 225. We have to first find out which is the smaller number. Here we can see 135 is smaller than 225. So, 135 becomes our divisor. We will take 135 and divide 225. You can see that it is going one time 135, and when we subtract normal division we get 90, but 90 is not equal to 0. So, we will take up 135 again and we will divide and see we get here remainder as 45. 45 again is not equal to 0. So, we will take up 90 again and divide it. So, we find that 45 2 times gives us 90 and we get the remainder as 0 here. Because remainder is 0, the divisor at this step is the highest common factor of these two numbers. How do we express them? We will write down 225 is equal to 135 into 1 plus 90. Again 135 can be expressed as 90 into 1 plus 45. We can take up 90 again and write down as 45 into 2 plus 0. Here the last divisor is 45, therefore, HCF of 135 and 225 is 45. Likewise, let us see the next question. Now students, this is your second part. Find HCF of 196 and 38,220. Let us see how can we find HCF of this. In this, as you know, 196 is less than 38,220. Obviously, I will take 196 and divide 38,220. Let us see, it goes one time 196. I think it gives us 8, 186. Now, I think I should try it 9 times. Yes. If I subtract, I get 8, and here it is 9 and 0 comes here. It is going directly by what is 196 into 5? Yes. We can see here in the first go itself I am getting the remainder as 0. In this case, I can express 38,220 as 196 into 195 plus 0. The divisor at this step is the highest common factor of these two numbers. So, we can write down HCF of 196 and 38,220 is 196. So, we have seen we have to focus on the remainder. In this, we got the remainder in the first division process itself. So, the divisor here is 196, therefore, the highest common factor of 196 and 38,220 is 196. Let us calculate the highest common factor of these numbers 867 and 255. As you can see, 255 is smaller than 867. Let us take this as divisor. Let us see how many times it goes. I think we should try with 3. Yes, 3 times it gives us 765. It goes 2 times. we have 51, and again we will take up 102 because remainder is not 0, and I think yes, now we get 102 and remainder is 0. So, the divisor at this step will be the highest common factor. How do we write down? 867 is equal to divisor into quotient plus remainder. Remainder was 102. In the next step, we had taken 255 and divisor was 102 into 2 plus remainder was 51. Again we had taken 102 and we had taken divisor as 51 multiplied by 2 times and remainder was 0. When the remainder is 0, the divisor at this step becomes the highest common factor. So, we can write down HCF of 867 and 255 is equal to 51. So, this is the method to calculate highest common factor using Euclid's division algorithm. Now, let us see the second question, which says, show that any positive odd integer is of the form 6q plus 1 or 6q plus 3 or 6q plus 5 where q is some integer. Using Euclid's division lemma, I can write down A is equal to 6q plus r. Here r obviously will be greater than 0 and less than 6 because I am using 6 as the divisor here. So, what are the possibilities? A either can be of the form 6q plus 0 or A is equal to 6q plus 1 or A is equal to 6q plus 2, A is equal to 6q plus 3 and A is equal to 6q plus 4 or A is equal to 6q plus 5. I cannot take A is equal to 6q plus 6, obviously it will be divisible by 6. So, these are the possible cases when I divide by 6. Let us look into the first case, A is equal to 6q plus 0. It is obviously 6q, which I can write down as 2 into 3q, which justifies that it is a multiple of 2. So, it is even. Alright. Now, in this case A is equal to 6q plus 1 seems to be odd. Okay. In the next one A is equal to 6q plus 2. Can I take 2 common here to write down 6q plus 1? Again it justifies that it is a multiple of 2 and therefore, it is an even integer. In the next A is equal to 6q plus 3, this is an odd integer. Next A is equal to 6q plus 4. In this if I take 2 as common, I get 3q plus 2, suggesting that it is again a multiple of 2, therefore, it has to be even. A is equal to 6q plus 5, this appears to be odd. Now, we can neglect these cases A is equal to 6q, A is equal to 6q plus 2 and A is equal to 6q plus 4 because they are even. So, by neglecting six q plus 2 and 6q plus 4. What are we left with? We are left with the cases 6q plus 1, 6q plus 3 and 6q plus 5, thus showing that any odd positive integer can be expressed in the form 6q plus 1, 6q plus 3 and 6q plus 5. Let A be any odd positive integer. Using Euclid's division lemma, I can express A as 6q plus r in this case and r is obviously greater than or equal to 0 and less than 6, because when you divide by 6, what are the possible remainders? Possible remainders are 0, 1, 2, 3, 4, 5, and thus a can be expressed as 6q plus 0, 6q plus 1, 6q plus 2, 6q plus 3, 6q plus 4 and 6q plus 5. Let us examine each case. In the first one, 6q can be expressed as 2 into 3q, which is suggesting that it is even. In the second, you can see 6q plus 1 appears to be odd, 6q plus 2 I can take common, 2, and we get 2 into 3q plus 1, suggesting that it is even. Next also is an odd. Now 6q plus 4 I can take 2 common and I get here this again as an even integer. Last one is again 6q plus 5 is an odd integer. So, by neglecting 6q, 6q plus 2 and 6q plus 4, we are just left out with the 3 possibilities. What are they? A is equal to 6q plus 1, 6q plus 3 and 6q plus 5. Thus, we have shown that a being any odd positive integer, it can be expressed in the form 6q plus 1, 6q plus 3 and 6q plus 5, hence proved. Let us look into the next question, question number 3, which says that an army contingent of 616 members is to march behind an army band of 32 members in a parade. The two groups are to march in the same number of columns. What is the maximum number of columns in which they can march? Here maximum number is suggesting that we have to calculate the highest common factor of 616 and 32. Since 616 is greater than 32, we apply Euclid's division lemma and we can express 616 as 32 into 19 plus 8. Here, because r is not 0, r is 8, we again apply division lemma to 32 and 8 and we can write down 32 is equal to 8 into 4 plus 0. Here remainder is 0, therefore, highest common factor of 616 and 32 is equal to 8. Hence, maximum number of columns is 8. I hope you have understood this. Let us go to the next question, which says use Euclid's division lemma to show that the square of any positive integer is either of the form 3m or 3m plus 1 for some integer m. Let a be any odd positive integer. We can express it in the form 3q, 3q plus 1 and 3q plus 2. Here according to question, I need to show that square of these forms is again a multiple of 3. Let us see how we can do this. On squaring, let me take this as case 1, 3q whole square gives me 9q square. Here if I have to show it is a multiple of 3, what will I do? I will take 3 as common. I am left with 3q square, that is I am having it in the form 3m, where m is equal to 3q square. Let us take the second case. In this 3q plus 1 whole square. What is a plus b whole square? Let me write down the identity here. We have a square plus 2ab plus b square. So, it is 3q square plus 2 into 3q into 1 plus 1 square, which can be written as 9q square plus 6q plus 1. Here I can see that I can take 3 as common in first two terms and I can write it as 3q square plus 2q plus 1. Notice here I am expressing this in the form 3m plus 1. How? 3m plus 1, where m is equal to 3q square plus 2q. Is it clear? We have taken square of 3q plus 1. I get a square as 3q whole square plus 2ab, 2 into 3q into 1, plus b square, that is 1 square, that gives me 9q square plus 6q plus 1. And I see that 3 is common in these two terms. I can write 3 common and I get 3q square plus 2q plus 1 form, because I have to show that I can write in the form 3m plus 1, where m is equal to 3q square plus 2q. Now, third case, I get here 3q plus 2 whole square. Again, using the same identity, a plus b whole square, I will have 3q whole square plus 2ab, 2a into b plus b square. On simplification, I get 9q square plus 12q plus 4. Very interesting. Look here, 4 will create trouble when I take 3 as common. So, I will split this as 3 plus 1, and I can express this as 9q square plus 12q plus 3 plus 1. If I take 3 common now, I can write it as 3q square plus 4q plus 1, and plus 1 is again giving us 3m plus 1 form, 3m plus 1, where m is equal to 3q square plus 4q plus 1. So, we have seen, students, let a be any odd positive integer. We have to prove that square of this odd positive integer is of the form 3m or 3m plus 1. For that, let us take the 3 cases. What are they? 3q, 3q plus 1 and 3q plus 2. In the first case, 3q whole square, I can write it as 9q square, that is equal to 3 into 3q square. I have taken 3 common to show that it can be expressed in the form 3m, where m is equal to 3q square. Let us see the second case. We have 3q plus 1 whole square. We are using the identity to expand the binomial here. We have a square as 3q square plus 2ab, 2 into 3q into 1 plus 1 square. That gives me 9q square plus 6q plus 1. Here, if I take 3 common in the first two terms, I have 3 into 3q square plus 2q plus 1. That again can be written as 3m plus 1, where m is nothing but 3q square plus 2q. So, we have shown the second case also, it can be expressed in the form 3q plus 1. Now, in the third case, we have 3q plus 2 whole square. We can expand and we get 3q whole square plus 2 into 3q into 2 plus 2 square. On solving, we get 9q square plus 2 in 3s are 6, 6 2s are 12q plus 4. Here in this step, we should notice that if I take 3 common, 4 should be split as 3 plus 1, which I have done here, 9q square plus 12q plus 3 plus 1. Now, if I take 3 common in these terms, I am having 3 into 3q square plus 4q plus 1 plus 1, 1 was left here. So, I can express this as 3m plus 1, where m is equal to 3q square plus 4q plus 1. So, I hope it is clear. We can express square of any odd positive integer can be expressed in the form 3m or 3m plus 1. Hence proved. Let us look into the next question, which says use Euclid's division lemma to show that the cube of any positive integer is of the form 9m, 9m plus 1 or 9m plus 8. If I take a as any positive integer, then I can express it in the form 3q, 3q plus 1 or 3q plus 2. Let us see how we can solve these three cases and show that it is expressed in the form 9m, 9m plus 1 or 9m plus 8. Remember, I am not taking 9m, 9m plus 1 and 9m plus 8 because if I take this, I will have to prove it for all the 8 cases when the remainder is 0, 1, 2, 3, 4, 5, 6, 7 and 8. That will become lengthy. So, we are taking here because 9 is a multiple of 3, it will be enough if I take 3q, 3q plus 1 or 3q plus 2. Let us solve this using the 3 cases, cubing the 3 cases 3q, 3q plus 1 or 3q plus 2. Let a be any odd positive integer so that it can be expressed in the form 3q, 3q plus 1 and 3q plus 2. Remember, I had to show it in the form 9m, 9m plus 1 and 9m plus 8. For this, let us see the 3 different cases. Here, case 1, I will be taking 3q whole cube. What is a cube? It is 3 into 3 into 3 is 27 q cube. Because I have to show it in the form of 9m, let me take 9 outside. I will have 9 3s are 27, that gives me 9 into 3q cube, showing that it is of the form 9m, multiple of 9, where m is equal to 3q cube. In the second case, we have 3q plus 1 whole cube. Here, I hope you remember what is a plus b whole cube. It is a cube plus 3a square b plus 3ab square plus b cube. I will use this identity to expand this. Look here, we have a cube plus 3a square b plus 3a b square plus b cube, that is 1 cube. On simplification, that gives me 27 q cube plus 9 3s are 27 q square plus 3 3s are 9 q plus 1. Let us see if I can express in the form 9m plus 1. Here, can we take 9 common? We will have 3 q cube plus 3 q square plus q plus 1. Yes, I could express in the form 9m plus 1, where m is equal to 3q cube plus 3q square plus q. Now, let us look into the third case. We have 3q plus 2 whole cube. Again using the same identity, we have a cube, that is 3q cube plus 3 into 3q whole square into 2 plus 3 into 3q into 2 square plus 2 cube. That gives me 27 q cube plus 3 to the 9, 9 to the 27, 27 2s are 54 q square plus 4 3s are 12, 3s are 36 q plus 8. Yes, 8 is coming. We have common 9 in these terms. So, I have 9, 3s are 27. So, it gives me 9 common 3q cube plus 9 6 are 54. So, 6q square plus 9 4s are 36 plus 8. So, I have expressed this also in the form 9m plus 8, where m is equal to 3q cube plus 6q square plus 4q. So, students, did you see I have expressed the cube of any odd positive integer in the form 9m, 9m plus 1 and 9m plus 8. Let me just explain you here. In the first case, 3q cube, we got 27q cube, taking 9 as common, we got 3q cube, which I could write as 9m, where m is equal to 3q cube. In the second case, I had 3q plus 1 whole cube. Here, on expanding, I get 3q whole cube plus 3a square b. That gives me 3 into 3q square into 1 plus 3ab square. So, 3 into 3q into 1 square plus 1 cube. This on simplification gives me 27q cube plus 27q square plus 9q plus 1. Notice that I can take common as 9 in the first 3 terms, which gives me 9 into 3q cube plus 3q square plus 9 plus 1. That means I can express it as 9m plus 1, where m is equal to 3 cube plus 3q square plus q. In the third case, 3q plus 2 whole cube, in the same way we have expanded and we have got 27q cube plus 54q square plus 36q plus 8. Notice that if I take common 9 from the first 3 terms, I get 9 into 3q cube plus 6q square plus 4q plus 8. That gives me in the form 9m plus 8, where m is equal to 3q cube plus 6q square plus 4q. Hence, we could express any odd positive integer on cubing can be expressed in the form 9m, 9m plus 1 or 9m plus 8. So, students, after completing our first exercise, let us have some homework here. I have assignment for you, just 3 small questions. First question is based on Euclid's division algorithm to find out HCF of 960 and 432. Second question, show that any positive odd integer is of the form 4q plus 1 or 4q plus 3, where q is some integer. And third question goes, what are the possible values of remainder r when a positive integer a is divided by 3? I think the questions are very easy. Please give them a try. We shall discuss in the next episode. Thank you.